that says binary information. If you guys want to jump in there with me, the first thing I want to grab is this PowerPoint. And I'm going to open it. I think this is one of the very first PowerPoints I made when I started teaching. So it gets a little whacked out in some places because it's hard to ever go back and fix those kinds of things. I'm ready. When I taught high school, we do this at the very beginning of the semester, and one semester a girl stood up and started screaming and was like, math, I ain't doing no math in the computer class. I live, Southwest Missouri, that's how people talk. And threw stuff around, and I said, well, try it, it's just really easy. And by the time we got done, she was very excited that it was that easy. I've got to print out some of these worksheets for us real fast. This little practice sheet, and I'll get one for everybody. I forgot. We don't print stuff out very often.
Easy. Really forever. I bet. That's a lot of work.
I was following.
Look at you, I thought of a pencil and everything.
I was following the tutorial, and it still took me.
Let me print one more.
Hey, ma'am, I need homework. My bad. Hey, forget the
I'm gonna print one more.
Never mind.
We got it.
You got it?
One on this row.
Oh, was there extra? Awesome. Thank you. You don't even need that one then.
Lesson 2 is grayed out canvas.
So go to your modules, and in lesson 1, you're looking for things that have the little circle, and you need to go in and click the mark as done button. Click the mark as done button on those things. So there's about 3 things there. You should see a little circle over here on the side of the items that need that. Mine are done. That's why there's a green check mark instead of the little circle.
Okay, I see the mark.
You see it?
Yes, thank you.
Anybody else having trouble seeing lesson 2? So we can make sure you're in there. Remember, once lesson 2 is open, we want to look at the overview. Prelude to Programming Chapter 2 is what we're doing with this lesson. Make sure you're clear on our objectives and mark that as done so it won't be blocking you from lesson 3. Get that one marked off. And then when you open the info, it should mark that one. You do have to also view the textbook PowerPoint. Again, like you saw last time, as long as you open it, that'll satisfy that requirement. Okay, we've got everything now. Back to where we were. Why do we talk about binary? Well, when computers first were being thought of, they've been thought of since the 14 or 1500s. People had different ideas about how to make mechanical devices do math, right? So lots and lots of ideas have come up over the years. Vacuum tubes were actually what was used originally for the very early computers. And with vacuum tubes, they generate electricity, or when electricity is going through them, it's either going in a clockwise motion or a counterclockwise motion. And the early engineers thought, how in the world could we save data in that kind of mode where we only have two states, like on and off, or clockwise and counterclockwise? How could we save data? And they realized that if they use the binary numbering system that only has two digits, 0 and 1, then that would be a way for them to be able to use electricity to store things and to keep track of things and do calculations. So binary is super important because we wouldn't have computers at all if they hadn't made that, thought discovery. And we still save data like to our hard drives and in memory in different formats, non-decimal numbering system formats. So we need to be aware of those conversions going on behind the scenes, encoding data, turning it binary, decoding data, making it to where we can read it easily again. So that's always going on all the time. So when we're talking about binary, it's just a numbering system. And we use decimal, right? The decimal numbering system. And all numbering systems have certain characteristics. They use these unique characters, numbers, to express a value, right? We just write it down. And the base of the numbering system, decimal being base 10 and binary being base 2, the base of the numbering system defines how many different unique digits we need to keep track of some sort of information. And the base of our columns, whenever we're talking about numbering systems, it's important for us to back up a little bit and talk about exponents. And, if we write 10 to the power of 3, we might say 10 to the third power. 10 is our base, and 3 is our exponent value, right? And to calculate the exponential value, we multiply that base number by itself, exponent number of times. So 10 to the third power is the same as 10 times 10 times 10, which is equivalent to 1,000. So we have to do some basic math, get ourselves thinking about these numbering systems to do this. So when we're using a numbering system, we use the column, the place value of the digit to know what it's worth, right? So each column has its own place value. Those place values are determined scientifically by taking the base of the numbering system to a given power. So our least significant digit, the rightmost column, is the base of the numbering system to the power of 0. The next one is the power to the first power. I'm getting all tongue-tied. And let me show you so it makes more sense. Numbering systems are formed this way. So let's look at base 10. Then it'll make more sense what I'm saying. Base 10, we use 10 unique digits to express a value. Our 10 unique digits are 0 through 9, right? So using those digits, we can express pretty much any value that we want to. 10 is the base of each of our columns, and taking that base 10 number to those exponential values is what gives us our ones column, our tens column, our 100s column, because the ones column is 10 to the power of 0, and any number to the power of 0 equals 1. So we always have a ones column no matter what numbering system we're using. The next column over is 10 to the power of 1, and any number to the power of 1 equals itself. So that gives us a tens column. The next column over is 10 to the power of 2, or 100. 10 to the power of 3, or 1,000. So that's how we get all our different columnar values in our base 10 numbering system. We learned that when we were little kids in first grade or whatever, that if we have a 6 in our ones column, it's equal 6. If we have a 6 in our tens column, it's equal 60, right? So we know those place values and those digits. Think about it. If we have this number, 3,486, we know it's written in base 10 or decimal. Internally, we could place those digits under their appropriate columns. We have a 3 in our thousands column, a 4 in our 100s column, etc. We do this automatically in our brains. We don't really even have to think about it. But since we have 3 in our thousands column, we know that's equal to 3,000. And 4 in our 100s column is 400. And 8 in our tens column is 80. And 6 in our ones column is 6. So internally, we're doing this math without even realizing it. We know then that this number is equal to 3,486 because of our columnar placement and our columnar values. So we could think about it some other ways too. We could write this number several different ways just using decimal notation, 3,486, or we could say this number could also be expressed as 3 times 10 to the third power plus 4 times 10 to the second power. We could make it really complicated like that to express that number. Or we could have another formula down like this, where we say it's 3 times 1,000 plus 4 times 100, etc. So we use base 10, we use decimal all the time. We do that math in our head. We don't even think about it. So what's base 2 and how is that different? Well, base 2 or binary, we only use 2 digits to define a value. Our 2 digits are 0 and 1. 2 is the base of each of our columns. And again, this works really well with electronics because we could say 0, a binary 0 is when the RAM is off, it doesn't have power. And binary 1 is the electricity is on, it does have power. So we can equate binary to electricity states very easily. Now, some terms, you've probably heard these and you already know what they mean. One binary digit is a bit. So if I have a number 1011 in binary, that is 4 bits. 8 bits are a byte. So this number is 1 byte. It normally takes 1 byte for us to represent 1 character of data. So if I'm going to represent a letter A, it would take me 8 bits, 1 byte. 4 bits are a nibble, a half a byte. We don't hear that technical term too often. I like to bring that one up. And when we're writing down binary numbers, the zeros at the front, the leading zeros, are insignificant. We can leave those out just like we could when we're writing a decimal number. We don't care about those zeros that come before our significant digits. Now, again, to create our columnar values, we can use the powers of 2. The ones column, our very first column, is 2 to the power of 0. And since any number to the power of 0 equals 1, that's our ones column. The next column over would be 2 to the power of 1, which would equal 2. The next column over is 2 to the power of 2, or 4. The next column over is 2 to the power of 3, or 8. Now, cool thing about binary, if you notice, those numbers are doubling as we move across our columnar values. The powers of 2 are actually really neat. And we use them a lot in computers, whether you realize it or not. So if you look in the middle here of 10 to the power of 0, that gives us 1. If we look at 10 to the power of 3, ooh, I want powers of 2, not powers of 10. let's go back. I'll open this spreadsheet from Canvas. It's finally opening. So when the early designers were working on this, they were like, man, geez, if we have to have 8 bits to hold 1 character of data, that's going to be a lot. You know, we're going to need to keep track of a lot of different bits. How are we going to handle this? How are we going to do things? And they started thinking about doing things in chunks. And they said, well, you know, if we had 10 bits of information, that would be 2 to the power of 10, and that equals 1,024. They named that a kilobyte. A kilobyte, that term did not exist before, but the term kilo did, and a kilo is about 1,000 pounds. And they were like, this is close to 1,000, 2 to the power of 10, if we have 10 bits. So we'll call that a kilobyte, so 10 bytes. Next, 2 to the power of 20 gives us about 1,000,000, so they named that a megabyte. And if you notice, math-wise, that's exactly 1,024 kilobytes. 2 to the power of 30 gives us about 1,000,000,000. They named that a gigabyte. And again, if you notice the pattern, a gigabyte is 1,024 megabytes. Next, 2 to the power of 40 gives us about 1,000,000,000,000, so we call that a terabyte. And again, a terabyte is 1,024 gigabytes. So because these are all based on the power of 2, that's where these numbers come from that we use to measure how much storage we have, how much memory we can use, and all those kinds of different things. So binary has been super important to us as we go with the development of computers. So here, this chart is a little messed up because it's showing us the powers of 10. So again, we see a kilo is close to 1,000, and that's where all of those numbers came from. Let's see, after terabyte, we'll have petabytes, and you guys should be seeing petabyte hard drives before too long. Beyond that, we have the exabyte, the zettabyte, the yottabyte. So as you get older, I remember when I was your age, we used to laugh about how someday there would be hard drives that were in the gigabyte range. And now those are pretty old because we're in terabyte range. But if we worked for a large corporation, we would see that they might have yottabytes of storage on their storage facilities, depending on what all they had to process. So we can see some really big numbers. Okay, so somehow the system has to go through some sort of encoding and decoding process. We have to take a number that's decimal and turn it binary, or we have to go the other direction. And we're going to start with binary to decimal because it's the easiest. So when I begin, I'm going to start by writing down the powers of 2. I'm going to start over here at the beginning with 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, because underneath that, I can put what the decimal equivalent is of a number in that column. Now, when I took my very first certification test, you guys will do it a lot as you become more involved in the field. I had to do some binary conversions, and I hadn't done any in, years and years. So I sat down, and they always give you a piece of paper or a little whiteboard that you can use to make your own notes. And the first thing I did was write down the powers of 2, because I couldn't remember exactly how to do it, but I knew it always was dependent upon my powers of 2. In this example, I have 1, 2, 3, 4, 5, 6, 7 bits. So we would normally go to 8 bits. So 2 to the power of 7 would be 128. I can figure that out easy because they always double the one before. Now I've got my powers of 2 written down, and underneath that I have the decimal equivalent. So given the number in binary 10111, how would I go about converting that by hand to decimal? If I had a calculator, it would be super easy, but I wouldn't be able to use that on a certification test. I have to use only my brain. So the first thing I want to do is line things up. My least significant digit is my ones column. So I'm going to say, well, I have a 1 in my ones column. Next to that, I have another 1. So I'm going to place that appropriately under the 2's column. The next digit is also a 1. That would go in my 4's column. Now my next digit, as I get to more significant digits or bigger values, is a 0. So I'd have a 0 under my 8's column and a 1 in my 16's column. Now I don't care about these bits that are higher than that because this number doesn't have any bits in higher positions. So now I've got this lined up under my columnar values. All I need to do is add up the values, the decimal values of the places that have 1s. So I have 16 plus 4 is 20, plus 2 is 22, plus 1 is 23. So the number 10111 in binary is equal to 23 in decimal. All I got to do is just add them up. Come back, ones. There they are. So pretty easy as long as I have my powers of 2 written down. Let's do another one. For 11010, again, I'm going to line my bits up, starting with the rightmost bit, the least significant digit, working my way to the left. My leftmost digit then would be my most significant digit, my LSD and MSD. Now, for this number, what is its decimal equivalent? 16 plus 8 plus 2. So I'd have 24, 26. And we are internally, we can do that math, but since it's binary, we don't really have to do much multiplication. The place value of our columns gives us the number that we need. So easy enough. What's this one? 100100. I'm going to line it up. 36. My 32 bit is on and my 4 bit is on. So those are the only ones I would need to add up. Pretty easy once we have our powers of 2 written down. Okay, do that half of the practice sheet thing. See if you're pretty clear on those. Do you want to tell me the form? See progress here on a piece of movement. So we're writing. We're doing this stuff. Pencils up there. We've got some. We've got some. So start on this side. Start writing them down under your columns over there, and then add them up. Put that away. Do you need it? Take it outside. How we doing? Get those numbers on that side.
Yeah.
So write your ones down.
Okay, so pretty much
Yep, pretty much, yep.
you work backwards.
Exactly.
0 right there.
That was kind of perfect. So 8 + 2 + 1.
Okay, just same place that has one.
Any place that has a one.
Okay.
Exactly. I have a few pencils if anybody needs one. Pretty easy once you get the hang of it. We were doing that other side. We're doing by hand.
Oh.
Oh.
If you're figuring out how to do those others, you like.
Whoops.
Over now.
Have you?
Yeah, I've done.
You've done it.
Yeah.
So, like, for example, so you know, this one starts on right, so we know we have a 1 here, 1 here. The revenue we do all.
I see people leaving now, yeah. Now remember, if you were taking a certification exam, you would not be able to use a calculator to add these numbers up either. You would not be able to use a calculator at all. So I want you to be prepared to be able to do that.
We always start from right, all the ones that have 1.
Okay.
So 1, 2, 8. This one. Right. Yes, this is
Okay, let's go the other direction then. some people are already just on it. Now we say we have a decimal number and we would like to convert it to its binary equivalent. Again, we're going to start by writing down the powers of 2. Starting at that least significant digit and working our way over. Then the number that we need to convert, in this case 21, we're going to start at the left side instead of starting at the right side like we did before. We're going to start at the left side and find a number that is equal to or smaller than the number we have to convert. So for my 21, the very first, the most significant digit that goes into 21 would be 16. So I would turn on my 16-bit. It fits in the 21. When I turn on my 16-bit, then I've accounted for 16 of the 21, and that leaves me 5 left. 8 won't fit into 5, so I would make my 8-bit 0. 4 fits into 5, so I would make my 4-bit 1. That would account for those 4, leaving me 1 left to convert. So my 2-bit would be a 0, and my 1-bit would be a 1. So decimal 21 is equivalent to binary 10101. Let's do another one of those. There are lots of ways to do this. This is not a super scientific way. That's like the easy way. So here I have the decimal number 14. What's the highest digit that would fit into 14? My 8. So I'll turn on my 8-bit. That leaves me 6 left to convert. So 4 would fit. I'll turn on my 4-bit. That leaves me 2 to convert. So I'll turn on my 2-bit and I'll put a 0 in my 1-bit because I'm done. So a couple of things that we can see right away that the computer can use to kind of check things. Sometimes behind the scenes, there will be some double checking going on, like if something is written to your hard drive. In this case, we had an even decimal number, so we know the 1-bit should be a 0. So we can do things like that to double check to make sure we've got it right. How about decimal 36? What's the highest order bit that I would turn on? 32. That would leave me 4 left, so I could zero out all of the remaining bits except for the 4-bit. So decimal 36 is equivalent to binary 100100. So it's a little bit harder because we have to do division instead of just lining up our bits and adding them up. See if you can do the conversions on that column, converting from decimal to binary. Do we have one more? I think there's one more. That's a big one. Oh, that's it. Okay. Any questions with that one? We have our people that have done it before, just now. This is binary. So we're seeing how you need to know whether this is a binary. Because otherwise you if this is right. Right, they're 2 different numbers. If you're starting out with 3, that's one number. Right, so if you took, if you took this number, work it back. Sometimes we do that, so that's great, no, you're just thinking about the patterns. Yeah, it is.
Yeah, but like it's kind of the same way that you could find that instead of like how did you go? It's like start from 0 all the way to F because F stands for 15.
Now, do you need help? We've got people back here who have done it before, they're experts. They can explain it to you using a little bit different words than I did, which might be exactly what you need. So like, we
It's like you have a whole yeah. Yeah. Flushing bacteria. Yeah. Sort of. So like what's the 3 right here? Okay. So what you're going to do is you're going to look through all of these and you'll see which one is the closest to the number without being greater than it. So 3 that would be 2. But I'm looking at the decimal value of that. Basically trying to minimize the amount of one you're using. Yeah. You're looking at the decimal value. 130. Also the 8th one is 128 and the second one is 2. So you're going to try to minimize the amount of ones you so basically, instead of doing 1, 1, 0, 1, 1, the 130 you just do 1, 0, 1, 0, 0, 0, 0, 1, 0. So that just equals 130 less. Basically, you know, you ever play the game where you're trying to get it to minimize the amount of eggs into like the pyramid thing? You know, you got like, so you got every kind of Cracker Barrel? Yeah, Cracker Barrel, yeah. So, like that, but you're doing it with numbers. You're trying to minimize the amount of ones you get to the number. That's how you do it, essentially. Like for 130, instead of doing like a bunch of different ones, you just try to minimize the amount of ones. So instead of doing 1, 0, 1, 1, try to get the same result, you just do 0, 1, 0, 0, 0, 0, 0, 1. That equals 130 plus. That's what it's for. So we're trying to make the decimal value come here equals whatever number will work. Yeah. Yeah. It's simply this 128. It would be okay. So then you take that and then all the other ones you call them zeros, and then that's your number. Yeah, for example, 99. Basically, or every gate needs to get 99 that's on over it's 64, 32. And also, I like to equal 96 plus 1 and 2. So it'd be 1, 1, 0, 0, 0, 1, 1, 0. You just got to minimize the amount of ones. They're going to all this, and you pick up ones that add the number and then over. Thank you guys. So, yeah, 69. So,
This state or city or maybe Utah, I'm sure. This is
and that's like it goes so 1 to 9 is now, you know, you're dealing with 1 to F. It still has up to 1.5, it's still right down, say 31 and the action on it at the
Oh no, I'm figuring it out. My brain's just slow.
Sometimes it's just a lot better when you try it. Okay, so how could you check to see if you had the right answers?
do it again.
You could do it again. You could also use the Windows calculator. Let me show you. Now, when you look at the Windows calculator by default, it's this little guy. Windows 10 has that new calculator too, so I don't know if we have that loaded on these machines, but at home, the Windows 10 calculator is the same way. If you look at your view, you can change the view to programmer. When you change the view to programmer, now you have numbering systems over here on the side. So right now, I have decimal selected. I'll type in a number, 78. I want to convert that to binary, so I can just click this BIN radio button and it will convert that to binary for me. Now, when I have binary clicked, if you notice, I only have the 1 and 0 digits to enter. So let's see, I'll clear it. And let's say I have 111,000. I can convert that to decimal just by clicking decimal. Okay, now the Windows calculator doesn't just have decimal and binary. If you notice, it has 2 other numbering systems. At the top, it has hexadecimal. Hexadecimal is base 16. In base 16, we have 16 unique digits to define numbers. So we add digits. We use the letter A to be 10, the letter B to be 11, the letter C to be 12, T to be 13, E is 14, F is 15. That gives us 16 digits from 0 through 15. So in hex, I can store really big numbers in a really small amount of space. With binary, it's the opposite. I have this regular size number, and when I convert it to binary, it becomes huge, all these digits. So hexadecimal is a really nice, compact way to save things using base 16. With base 16, you can see once I have it clicked, the letters show up on my calculator. So I could say, well, I have 78CA, and I can convert that to decimal by clicking DEC. So the Windows calculator will do all those conversions for us. The other one is octal. Octal is base 8. We don't see it used a lot. Some early computer systems used base 8 to try to be like a happy medium between binary and hexadecimal. I think it was like Digital Equipment Corporation computers and some weird things. So you won't see a lot of octal, but you could actually see it around. Now, someone noticed that when you have numbers written down like that, it's really hard to tell if you have a decimal number or a binary number. You know, what format is it in? So you'll often see things like that, indicators. If you see a number written like X10101, that's telling you that it's in binary. If we see a number with an H beside it, that's telling us it's written in hexadecimal. And you're going to see different schemes for doing that, for letting you know what numbering system a number is written in. But you can usually find some sort of clue like that somewhere in the documentation. So you can use your Windows calculator to check your answers, make sure you're right. Whenever you're using the fancy Windows 10 one, it's still a view setting. It just looks a little bit different, but you still have the programmer view that you can go into to have the different numbering systems. So you can double check your answers. And then lastly, we can do some competition with the binary game. The binary game here, it says I have a number 21 and it's given me these 8 bits. So very quickly, I would need to click which bits should be turned on to make it equal 21. It already had them highlighted for me. And it should make that go away. Oops, wrong. Now this next one, it has bits already highlighted. So I need to type in the decimal equivalent. So it goes both ways in the game. So this would be 2426. See if I can type that. And it kind of, it's like Tetris. If you get it right, it will go away. We type it. There used to be a better game that the Cisco Academy had, and then they made it where you couldn't use it free. So this is kind of somebody else's idea of it. It's a little bit clunky, but I'd like to try it, practice it for a minute, and then we'll have a competition. I'll find a prize.
It'd be a lot better if you could type it.
Yeah, wouldn't it? It's really hokey the way it jumps to that kind of number pad screen. I didn't like that, but it's the best one I could find.